Okay, so the next speaker is T.Grava from Bristol and CISA, whose title is too long to say, but it's up there. So.
Okay, so thank you, well, the organizer and particularly Filippo for putting all this crowd together. So today I'm going to speak, about the anharmonic oscillator. And as you can see, the title, Foucault points and a conjecture of Shapiro and Tater. And this project came out after Shapiro came to CISA and gave a talk on this problem. And so myself and Marco Bertolo decided to put a PhD student, Eduardo Chavez Serine, on this problem, and these two papers came out. So the first part of the talk, I'm going to talk about this conjecture of Shapiro and Tater. And then out of this work, some observation came out that has to do with the Stilty-Foucault problem. Okay, so what is the problem? So we consider the Painlev 2 equation. This is an ODE in the complex domain for a complex function u, and t, it is a complex parameter. And this equation is nonlinear, and it has a rational solution only if this alpha, this free parameter here, is an integer. And the rational solutions are parameterized by this expression here, where y are what they're called Voroblev-Jablonski polynomials. And they are of degree n times n plus 1 divided by 2. So they have a recursive formula of this expression. So, and it's non-standard, where the recurrence is set up by setting the first equal to 1 and the second equal to t. Otherwise, there is an expression in terms of Schur function, we are staircase partition, and given by this expression. So they have a closed form expression. So this polynomial, so you take the logarithmic derivative of the ratio of two polynomials, and these are all the rational solution of the Painlev 2 equation. So an observation that was first done by Peter Clarkson is that if you look at the zero of these polynomials, they form regular partners in the complex plane. So they set in these triangular domains. This was an observation. And this was explained later by two groups, Buckingham and Miller, and Bertola and Botner. And they give an asymptotic description of this zero. Okay, so this is one problem, and the next problem is the following. I want to put this point in the complex plane in connection to another problem. So the second problem is the following. I'm considering the spectrum of this Schrödinger equation with quartic potential, where t is a complex parameter and j is also a complex parameter. And we fix this following boundary condition. So we are Schrödinger equation in the complex plane. And I'm setting this boundary condition, so I want that y goes to 0 in 3 directions in the complex plane, pi and plus minus pi over 3. So this problem has been studied quite a lot, and there is some terminology that is the following. So the spectrum is called quasi-exactly solvable, and if a part of the spectrum is exactly solvable. So not all the spectrum are part, and is explicitly for j, and is explicitly for j in n. And so if we have two boundary conditions, this is only 2 out of 3, this spectrum is quasi-exactly solvable. Well, if I put 3 boundary conditions, the all 3, so all 3 of them, all the spectrum is explicit for when j is in an integer. So it's what we get. So you take j integer, then all the spectrum of this operator is explicit. And so let me get to the observation of Tater and Shapiro. So if I take j integer, then the equation, so the quartic anharmonic oscillator, has this kind of quasi-polynomial solution. So it's a polynomial time an exponential, where the exponential is this cubic polynomial. And so if we plug these answers into the Schrödinger equation, we come up with this second order equation for the polynomial P. So this is an operator acting on the space of polynomials. And then I can write it as a matrix, as I can write it in this matrix form. So this is as 4 diagonals. It's an operator with 4 diagonals, not 3, 4 diagonals. And the eigenvalues are just the characteristic polynomials of this matrix, okay? And so the question that Shapiro and Tate ask is which are the values of T complex such that we have double eigenvalues? So this was the question. For which value of T, this discriminant is basically equal to 0. So I want the determinant equal to 0 and also the first derivative. So this was the question. And their observation was the following. Okay, so they found here, so we plot the 0. So there are two dots that you can see, the red and the black. And what they observe is that the red are the roots of the Jablonski polynomial, and the black are the roots, the value of T for which that discriminant has 0 values. So for which we have repeated eigenvalues. And so as you can see, they are very well on top of each other. So, and this was, so what we try to address is why this is happening. Okay, so why we have repeated eigenvalues. So is the problem clear? So, okay, so now I'm going to explain why this is happening, and for explaining this problem, so we have to study a little bit more the property of the quartic anharmonic oscillators. Okay. Okay, so I want to say that, I mean, so this is just to say that the problem is not trivial, because if you compare the polynomials, so this is the discriminant and the locus, and these are the Jablonski polynomials. So you can see they are different. So look even at this T10. So they are different polynomials. So the polynomials are different, but the roots, they're very close. Okay. And they have both of them this very regular lattice. Okay, so let me explain what's happened here. So it's a collection of structural problems on this quartic anharmonic oscillator. And so the first observation is that if I want to solve this Schrödinger equation with this 3 boundary condition at infinity, so this problem has a solution if and only if J is integer, and the solution is given by this quasi-polynomial, if and only if. So if I give 2, it's not necessary, but once I give 3 boundary conditions, the only solution are of this form, quasi-polynomial. And this quasi-polynomial satisfy, okay, you just plug these answers here, and it satisfies this second order ODE, okay? So this is the first observation. And so the second observation is that this polynomial has a little bit more structure. It's not only a solution of this second order ODE, but is a degenerate orthogonal polynomial, degenerate. So it means the following, that, okay, is defined by these usual orthogonal relation around to infinity to these 2 points, so these 2 paths. So it's going from this gamma and gamma tilde, so infinity 1, infinity t, infinity 5, infinity 3, where these are some constant, but the orthogonality relation has to run till n. So this is degenerate because we have an extra condition. So this is a way to characterize these polynomials. So these are degenerate orthogonal, not only orthogonal. Okay, so this is the first observation. So this is our polynomial, but are degenerate orthogonal, not only orthogonal. I will explain. Yeah. No, this is there is no relation so far. I just want to show that the 0 of the discriminant locus is the same. So it's not the same, it's asymptotically the same. They lie on the same.
The entire function, but this is polynomial. They related in the limit when the order of the polynomials go to infinity?
No. The statement, so what I want to show is that the statement is that the value, the statement is the value of the parameter t for which this ODE has a repeated eigenvalue, so double eigenvalue. They sit on the complex plane, so this t sits on the complex plane, and it sits on a regular lattice which coincides, which asymptotically is of the form of the lattice of the zero of the Jablonski polynomials, which are a rational solution of the Painlev equation. This is the statement. So you take t, complex number, you solve this quartic anharmonic oscillator, and you ask yourself when these are repeated eigenvalues. And the value of t for which this happens has the same structure of the roots of the Jablonski polynomials. In the limit, yeah. But this is done for n equal, I think, 30, and it's already very nice. Yeah, so n equal 30 is already very nice. Okay, so let me keep going. So I want to say, okay, so I'm building now a solution. So what I'm doing now is building a solution of this equation. So this is a quartic anharmonic oscillator. I'm building solution of this equation, and I'm saying that they have only this form here. If we impose these three boundary conditions, these P are polynomials, which are degenerate and orthogonal. So this is the observation. And okay, and the second observation is that if I want to have a repeated eigenvalue, I have to have not only the linear combination of these has to be equal to 0, but each single terms, each single integral, so from omega 1, omega 3, and omega 3, omega 5 is equal to 0, okay? So these are not two conditions because the sum of these two objects has to be equal to 0. So when the sum is 0, it's enough that one of the two is 0. And okay, so this is our characterization of this polynomial. And the third observation that's why we have some relation with vacated point is that the zero of this polynomial satisfy this vacated type relation. So this theta, I recall, is a polynomial of degree 3, which contains t. So we have all this collection of property of this polynomial. So they are degenerate, orthogonal, and on top of that satisfy this relation. Okay, so this is the characterization of the polynomials. And now let me try to explain what happened, why these zeros why the value of t for which all these conditions are satisfied, they sit on the same, they have the same structure as the zero of the Jablonski polynomial. So, and this is now, we have to do some asymptotic analysis, so for large n.
Can I just ask a simple question? So is the spectrum real at these t values?
Sorry?
Is the spectrum real at these t values that you're looking at? It's not, no.
This is on the complex plane. We are on the complex plane.
But the spectrum of the Hamiltonian is still complex. Because
well, it's a complex potential, so with this boundary condition, yeah.
But sometimes you get real eigenvalues even for...
Yeah, you can have real eigenvalue, yeah, but
these are not real, though, values at these points.
No, we are just
okay,
complex potential with this boundary condition at infinity, yeah.
Okay, thanks.
Okay, so the first... this is some results that have already appeared in the literature. So, so it's a characterization of the poles of the Painlev equation, Painlev 2 equation, and is given by the following. So each Painlev equation is described by a compatibility condition of a 2 by 2 linear system. And when we look at this linear system near a pole, this equation, the equation for Painlev 2, reduced to the Schrödinger equation with quartic potential. So if you take Painlev 1, you have the cubic potential. If you take Painlev 3, you have the Oin equation, the Oin equation, and so on. For each Painlev, you have a Schrödinger equation with some potential. Okay, so and this is what happened for Painlev 2. So if alpha, so in the case alpha, the parameter n is an integer, and we have that T is a pole with residue -1 of the Painlev equation. If and only if there is a value B here, such that the following second order ODE with this potential has this Stokes data. So this is an ODE in the complex domain, which have essential singularity at infinity upon carré rank 1, and then you want to study the monodromy problem. So this is the monodromy problem of this ODE, and you have some Stokes sector, and the Stokes matrix have this form. So we have this condition that was first studied by Novoksheno to reduce the problem of the poles to a second order ODE of this form. And the Stokes data for this particular solution of Painlev was calculated by Buckingham and Miller. And we can do the same. So now we can do the same for our problem. So this is the Shapiro-Tate potential, and for the values of T and lambda that belong to the Shapiro spectrum, so we have this Stokes data. Again, so in this case, there are three identities matrix, and this is follow from the fact that we have solutions that are these quasi-polynomials, and then we have these three parameters S1, S2, S1, S3, and S5 that has to satisfy this condition. So this is the Stokes data for this ODE in the complex domain, which has essential singularity at infinity. Okay. Okay. Now we have this extra condition to impose. So, and to impose this, we have to do WKB analysis. So I have to calculate now. So I have an ODE. I have to calculate the Stokes data and impose this condition. So to do this, I need to do some rescaling. So we rescale T lambda and the variables in such a way that this second order ODE can be written in the same form from the two cases. And the form is the following. So we have a quartic polynomial where S is now our parameter that has been rescaled. And so the H is different from the Shapiro-Tate and the Jablonski polynomials. And this is the quartic potential. Okay, so now we need to calculate Stokes data to impose condition on this parameter T, is the one that we want to calculate, and do our job. Okay, so for the Jablonski polynomials, we have so the Stokes parameter are defined, so are known, and so this is fixed. So if you do WKB analysis, we fix the value of S and E. That makes the job. So and so for the Shapiro and Tate case, we need to impose an additional constraint that is this one, that, as I said before, to have an additional degeneracy condition. Okay, so basically we have, so the point is we have to determine these values of S and E such that we get those Stokes data. That's the job. And Yeah, so there is some freedom, but I mean, this is basically what's happening. So there is various topological types of graph that you can find. So these tau 0, tau 1, tau 2, and tau 3 are the roots of the quartic polynomials. And there are several topological types of graph, but this is the only one that works when you do double KB analysis. So this is I'm not coming into details, but I mean, you have to do WKB analysis, introduce Voros symbol, make all the job, and you end up to having a graph of this type that is the only one that works and gives the right, all the conditions that we need to impose, they work. And so we end up with getting these two classes of quantized condition for the Shapiro Tater and the Painlev 2, the Jablonski polynomials. And they look, so this is the square root of this quartic potential between the various roots, tau 1, tau 0, tau 2, tau 0, tau 3, tau 0. There are no three conditions, there are only two of these independent, and the same here. And these constant, which are m1, m2, and 3 are integers. These are have to sum to m minus 1, and the same here. Okay, so this is our quantization condition that fix uniquely these two complex parameters, S and E, asymptotically. So this is leading order asymptotics. So we have two independent equations for two complex parameters. So you can get this parameter uniquely. And as I said, at first, these two conditions looks different. But so what we have is that if we solve, so we take a point S0, E0 that solve the equation in both cases, and we look what happened nearby when we move a little bit in a direction. So we have, so keeping that these two quantity parameterize the lattice and are the same for the two different problems. So it means the two different problems have the same lattice point, which are parameterized by this omega and omega prime. So if we look at near a point, so we took an S0, a solution of both equations, and we move a little bit around, and so the lattice size around this point is the same in the two cases. And so this is explain why these lattices are so similar. And this is the first, so the first observation, the first result. However, this is since we have rescaling by n everything, so the lattice distance is of order h bar, which is the rescaling we have. So h bar is of order 1 over n. And so this is still does not justify why the lattices are so close to each other. And this is, so what we can observe is that if we stay close to the origin, so if we look at points in this in the spectrum which are close to the origin, so for this parameter S and E that are close to the origin, then at this point we can say that the quantization condition that correspond to this choice of three integer values, m1, m2, m3, are the same for both the two cases, Shapiro and Jablonski polynomials, and they select out values of S and E, so S and E that differ by order of h squared, so is of size an order of magnitude smaller than the size of the lattice. So, and these results justify, so at least near the origin, justify the fact that these two lattices are the same. So we can say that the selection of this point, so the size of the lattice is of order h bar, and the points are chosen, so in the two cases are chosen of order of h squared. So the distance between the two is of order h squared. Okay, so this is all I want to say about the problem, but Let me, so how much time I have? Okay, so I have 20 minutes. So, so from this analysis, as I said, come up, so this is terminates the proof of this Shapiro-Tate conjecture. And now I want to pass to this Stilti-Fekete property that was observed while studying this orthogonal polynomial. So in particular, so what we observe is that the zero of this degenerate orthogonal polynomial satisfy this kind of Fekete type relation. This was the observation. And then the natural question is, this property is generic, so can we do it for any orthogonal degenerate orthogonal polynomial? And just to recall that this kind of relation was studied by Stiltian and Fekete for the classical polynomial. So if you consider the Hermite polynomial, so they are the zero of the Hermite polynomials are the Fekete points. I mean the points that maximize this functional. So the points that maximize this functional are exactly the roots of the Hermite polynomials, and they satisfy this what is called Fekete type relation. And similar relation holds for the other classical polynomial, Jacobi and Laguerre. Okay. So how much can we generalize this relation? So how much? So what is generalization of this relation? And so this example that we came up studying this degenerate orthogonal polynomial suggests to generalize this relation to this kind of problem. So we have this logarithm, I mean, so this interaction terms plus is equal to the ratio of two polynomials, which I called A and B, and these two polynomials has to be relatively prime, and B we want to be monic. And yeah, this is real. This is indeed, I call it X. So this is our orthogonal on the real axis, and this is typical of real. It's in the complex plane. This is a different problem. But it's a different problem. But I don't put restriction. You can put restriction, I mean, if you want. So you can ask. So this is on the complex plane. So the question is, I give you two polynomials, and I want to solve this equation. That's the question. It's a kind of a Fekete type problem. And yes, so you can consider this problem as the stationary point of this functional, where now this theta prime is relating to AB by this equation. So A plus B prime divided by B. Okay? So this is the question that came out naturally. And as I explained before, I mean, they were involve degenerate orthogonal polynomials. That was involved before. So now we generalize, and so this is what we are trying to solve. So so there is this review article by this bunch of people, Marcelin, Martinez, Finkelstein, and Martinez-Gonzalez, that they were asking the same question. So the classical Fekete problem is related to the zero of classical orthogonal polynomials. So the question is, can we generalize this problem to other families of polynomials? And in the case of the classical problem, this Fekete solution gives the global minimum. So you get a global minimum of the functional. So can we have other kind of equilibrium, stationary point, non necessary minimum? And so what is the appropriate model for the complex zeros? So if you take orthogonal polynomials which are not orthogonal on the complex plane, on the real axis, but on the complex plane. So can we have a model for complex zero? And we address this question with the following result. So the result is that there is a one-to-one correspondence between solution of this algebraic equation and what I'm calling maximally degenerate orthogonal polynomial of degree n for a semi-classical moment functional, which I call of type AB, that I'm now introducing. Okay, so for each of these problems, I can find a degenerate orthogonal polynomial. Okay, so let me explain what it is, the terminology. So I take two polynomials A and B, which are relatively prime, degree A and B each, and so I take a functional M from the space of polynomial to C, and this functional is called a semi-classical functional of type AB if it satisfies this relation. So you take a polynomial P, and the product of P with A must be, the moment of the product of P with A must be equal to the moment of P prime with B. And okay, this condition was widely studied, and the result is that a function that satisfies this property can be represented by this integral function, where gamma are some contour in the complex plane and SL are some complex numbers. And D here is the maximum between the degree of A and B minus 1. Okay, so in this case, for example, here is pictured the gamma, the contours gamma, in the case of B equal 1 and theta, so B equal 1 and theta is a polynomial of degree 5. So you have the region of the plane where this integral basically is convergent. So you have to take the Stokes line where you can have convergent. Okay, so this is the first definition. And now, if I have this functional, I can define orthogonal polynomials in the usual way. So you want orthogonality condition on these contours, and we can build the orthogonal polynomial with, defining the moments and defining the determinant with the moments. So these are the orthogonal polynomials with respect to this functional, okay? And now let me define what are the degenerate polynomials. So the polynomials are degenerate, and I call L degenerate if not only we have the usual orthogonality condition, but we have some extra orthogonality condition. And so L degenerate if we have that this moment is 0 from n to n plus L minus 1. So the 0 degenerate orthogonal polynomial are the standard condition of orthogonality.
The definition of inner products.
It's just the integral on the contour.
Over which contour? It's
Gamma.
A complex plane, right? It's a complex plane. So which contour?
Which contour? So are the contours. So let me do an example back. So if you take, for example, B equal 1 and A, so theta prime, theta of degree 5, you have to have the contours where this is convergent. So depends on the polynomial. So you have so the number of contour depends on the degree. It's the maximum between A and B minus 1. The number of contours that you can have. You can have also poles. So if B is a polynomial, you have poles here. So you have to take the contours where things are convergent. But okay, so now let me say what are the degenerate polynomials. So the degenerate, I say if you have extra orthogonality relation. And so if you take a polynomial of degree n, it's L degenerate. So looking at this Hankel determinant is L degenerate. Instead, if you have, apart from the usual relation, so this is the way, so usually when you define your polynomial, you have this condition, then here you put Z. So you need to have this extra condition here. So, and so if this Hankel determinant is equal to 0, then the polynomial is degenerate, okay? And so this condition, so since this moment contains the parameter, the weights, so this parameter S1, SD, and this condition is basically a homogeneous polynomial on the weights. So we have, so it means that we have to put equal to 0 a polynomial which is homogeneous in this way. So we have the freedom to choose these weights, which are complex number, and the condition of having degeneracy, it means just to put to 0 this polynomial, which is a degree n in the weights. Okay, so we have some freedom, that's what I want to say. If we have only one contour, there is no chance to have a degenerate polynomial. It's because we have many contours, we have freedom of choosing these parameters and to make the polynomial degenerate. So the classical orthogonal polynomial like Hermite, Laguerre, and so on are 0 degenerate, okay? 0 degenerate. And so the result is the following, so that, so if we have these points Z1, Zn that are the solution of these, that satisfy this configuration of equilibrium, so where A and B are relatively prime polynomials, then the points Zk, so Zj, are the zeros of a maximally degenerate orthogonal polynomial. So actually I forgot to say what is maximally, so let me maybe was, yeah, so maximally degenerate is when L, so the degeneracy, this number here is equal to exactly to d minus 1, where d is the number of contours, different contours that I have in my case. So just to repeat again, the classical polynomial are 0 degenerate. Okay, so the result is basically the solution of this equation is in one-to-one correspondence with the zeros of a maximally degenerate orthogonal polynomials for a semi-classical moment functional of type AB. And for fixed n, so here we have an equation and points, the number of critical configuration is n plus 1 to the d minus 1. And the quasi-polynomial, so if I consider this quasi-polynomial where theta, it's the weight is related to AB by this relation, they satisfy this Schrödinger type equation for a potential V that depends on A and B, okay? So, and vice versa, if P is a semi-classical maximally degenerate orthogonal polynomial of degree n for a semi-classical moment functional M of type AB, then it's 0 satisfy this equilibrium equation and this ODE and this ODE, this Schrödinger type ODE. Okay, so I think this is all I want to say. And
Are there questions?
A tiny question. So you have this maximal degeneracy that depends on a parameter that depends on the degrees of A and B, and it may be, for example, 2, say.
sorry?
When this parameter is 1, there is not much to say, but
No.
say that it is 2. So you're asking that Pn is doubly degenerate.
Yeah, like
What
the example in the Shapiro-Tate case, that was W, yeah.
What if instead you ask that Pn is 1 degenerate and also Pn plus 1 is 1 degenerate, which seems to have the appropriate number of degrees of freedom as well, right?
This is, yeah, this is so.
Maybe Pn and Pn plus 1, they're not so different. So asking that Pn plus 1 are degenerate simultaneously is not very different, but it seems to be a bit nicer at the algebraic level of the determinants to vanish, because once the first one vanishes, the second one vanishing, once you write it with the Schur complement formula, is a very tiny expression, if I'm not mistaken.
Yeah, yeah, no, yeah. So, but this, yeah. So we didn't think it's a different question, but
Yeah, it's completely
yeah,
different. It's
yeah, yeah,
going
yeah.
in a different direction.
Yeah, it's bringing to a different. Yeah, no, thank you. We didn't think about it. Yeah.
So I have a question. So you have this connection between this anharmonic oscillator and this sort of quadratic relation for your polynomials. I mean, those are the two sides of the connection. But this looks, this sounds like a manifestation of the ODE-IM correspondence, or at least it reminds me of that. Do you know what I'm? So this connection between ODEs, in particular anharmonic Schrödinger equations, and some quadratic relations associated with an integral model. So,
This is a
but this is
kind of Bethe equation, no?
yeah, but is this a manifestation of this correspondence that's been studied, which is called the ODE integral model correspondence? Or?
Yes, I don't know actually. I mean, so.
Okay, because that also grew out of the work of Bender and.
So yeah, but I'm hearing twice.
I mean,
so it's
there's feedback, is there?
yeah. Yeah. So I'm really.
So the discovery of this correspondence also came from the Bender Botcher paper as well, was motivated by that. So this is work of Lukianov and Dorian, Tateo and people.
Yeah. But I mean, But I mean, I think the observation. So this kind of equation has been studied a lot, in Bethe answers. So our observation is that this is the zero of the degenerate orthogonal polynomials. That's our observation.
Okay.
So these are typical equation in Bethe ansatz, but I don't think we are not aware that anybody observed that the solution are zero of the degenerate orthogonal polynomials. That's the message.
Oh, okay. Thank you.
We show this pictures of zeros, terminal zeros. The second slide.
Maybe, so I have to go.
At the corners, what is the asymptote at the corners of envelope? So let me consider an envelope. And then, is this an angle or it's cusp?
Yes, so the asymptotic and the boundary is different than in the bulk.
But is this a cusp or angle? Corner. It could be corner or cusp, right? What is it?
It's a cusp.
It's a cusp.
Yeah.
It's a 2/3 cusp. It's a
2/3.
major elliptic cusp.
Yeah, because here is elliptic function, and yes, it's a cusp, and it has a different asymptotic. Yeah.
There is a very close analogue to that, which I may mention private, which is related to what is called Laplacian growth, and then it's very similar picture, and also related to orthogonal polynomials, which measure is not located on the contour, but in the entire complex plane. This will produce.
Yeah, thank you. Yeah.
Any other questions? Yep.
So you said the error was expected from the theory in 1/n squared. Did you check on the numerics that it is really 1/n squared, or maybe it is smaller and that it is smaller?
Say it again, 1/n squared? No.
1/n squared, I think at a point you were saying that the error that you find.
Yeah. So I want to say in this, so you see these points here, they are not on top of each other. So what we are able to prove is that not near the origin, we are able to prove that the point, so the distance between these points is of the order 1/h, let's call it h bar, which is 1/n or 1/n plus 1. So this point near the origin, so the blue dots and the red dots are distance, the distance is 1/n squared, is what we are showing.
So what you prove is tied with what is true numerically.
Yeah.
That's what the question maybe the numerics was even better in principle.
Yeah, no, what we can prove in the, not near the origin, so not near the origin, so a distant h bar, so a distant h bar near the origin. So what we can prove here, not near, so it's only that these points are the same lattice, but we are not able to show that their distance is of the order 1 over h squared. So the distance between each point is of the order, sorry, h bar, sorry, not 1 over n, yeah. But not at the point, yeah. So it's surprising, but the fact that on top of each other is surprising. So, because we are not able to prove it. We are only able to prove it near the origin. Yeah.
Any other questions? Nope. Okay, let's thank Tamara again. Thank you very much.
Thank you.